All right, so today we're looking at the shortcut rules for differentiation. Hopefully these are going to make our life a lot easier. We don't have to use the long limit definition. Question, yes? Let me address that at the end of the class, okay? Okay, so we're talking about the shortcut rules for differentiation, starting with the derivative of a constant. Remember, derivative, d over dx also represents the derivative. So I could write, like, for example, I could either write dy over dx. I haven't used that notation that much so far. Just know that this is nothing different than writing y prime of x. So y prime represents the derivative of the function y. Also, I could write dy dx, which means the derivative of y with respect to the variable x. And you know, that notation is actually especially helpful because it's kind of like delta y over delta x, except that we're taking a limit as that increment delta x is going towards 0. But just know that d over dx also gives you the derivative of something. It's just another notation to do the same thing. Okay, so speaking of the derivative of a constant for our rule number 1. And if you've seen these rules before, would you please refrain from answering, because then I think it's really easy for you guys. Let's try to have everybody else, those who haven't seen calculus before, think a little bit harder on these. What do you think is the derivative of a constant? A constant function would be just like a horizontal line, something like, say, 5, y equals 5. What do you think is the derivative of that line? Or the slope of that line, right? That's what a derivative is, right? For a line, it's easy. For a curve, we have to do more work. But what is it? What is the slope of that line? Anywhere you are. It's 0, right? So basically, let's make a note that derivative of a constant will always be 0. Because that's like finding the slope of a constant line, a horizontal line, okay? How about rule number 2? Say that you have the derivative of mx plus b, which is a line, right? Mx plus b represents a line where m is the slope of the line, right? So what do you think is the derivative of a line, a slanted line? Any thoughts? I heard a good suggestion already. Any other suggestions? For a straight line, it's really easy to find instantaneous rate of change, right? At any given moment, it's always the same, right? Rise over run is always a constant, no matter where you are on a line. And what is that constant equal to? The slope, m. So the derivative is going to be that slope, which is m. By the way, we could easily use the limit definition to prove each one of these. All you have to do is like take x out, replace by x plus h, etc. Go back to the basic definition, and you will be able to show through analytical methods how these rules are derived. Okay, so if we have just a line mx plus b, the derivative is going to be its slope, because for a straight line, the slope at any given moment is a constant. Okay. What if you have something like x to a power? Now, we've already worked on some of these cases. For example, we've done if y equals x squared, what was the derivative there? dy dx or y prime was 2x. Okay. I'll give you a few more examples. If the function is x cubed, I don't know if maybe there was one question from the homework that used a cubic function. It gets really messy because you've got to extend x plus h to the 3rd power. They get very messy very quickly after the 2nd power. But let me just tell you at the moment so that you can see a pattern. It's going to be 3x squared, the derivative. I'll give you the next one also, so see if you can give me the general pattern. If y equals x to the 4, its derivative is, any guesses? 4x cubed. That is correct. Now, what about the general rule? If you have x to the n, what do you think will be the derivative based on these pattern we see here? Yes, Adam? Precisely, n times x to the power of n minus 1. Basically, if you had to write a rule for this, you would say, when we differentiate a power function, x to a power, you bring that power down and you subtract 1 from the power, and that's how you come up with the derivative, so you don't have to apply the long method. In a minute, I'm going to show you the analytical way to get that answer, okay? But right now, let's just do a few practice problems. For example, let's do the derivative of x to the 7. What is the derivative, d over dx, of x to the 7th power? Applying this rule that we just learned, a very basic rule, it's going to be 7 times x to the 6th. None of that long limit definition, much, much easier to do. What if we have this one? The derivative of 1 over x. How do we do that one? The derivative, d over dx, of 1 over x. Okay. When you have a situation like this, when x is in the denominator, to make it look like this rule, you needed x on the top, so rewrite it first. So before we differentiate, we're going to first rewrite this expression. So 1 over x is the same thing as x to the minus 1, right? Would everybody agree? Okay. Now let's apply the power rule. So you want the n times x to the n minus 1. So there's going to be negative 1 times x to which power? We need to subtract 1, so to the negative 2nd power. And on all of these examples, I will ask you to write your answer without any negative exponents, please. Okay, so if you can rewrite this again, how would you rewrite it? And don't forget the negative up front, so it's going to be negative 1 over x squared, right? Basically, the negative 2 exponent means bring that quantity down as a positive exponent as x squared, but extra negative 1 up front still remains. Now remember that question from the last group activity we had, I think it was a part D or something, like 1 over x. We did all that work to simplify right here in 2 seconds. The answer is negative 1 over x squared. So it's really a tremendous saving in time. Yes? Yes, because first you bring the power down, which is negative, right? And then you subtract 1 from the power, following directly this rule over here, right? So the power became negative 2. This negative still remains there. But the negative exponent, that's pushing the quantity to come into the denominator, so that's why we ended up with negative 1 over x squared.
Oh, because like 1 over x technically written as
that was the first step, right?
Yeah.
Right. Then we brought the power down and subtract 1 by 1. Right. Okay. Let's do the next one. Let's do the derivative of the square root of x. Once again, before we find the derivative, it helps to rewrite it as x to a power, because we're going to apply the power rule, which is rule number 3. So we're going to, first of all, rewrite it as x to the 1/2, right? That's what root x is. Notice that in that step, I kept my d over dx notation because I haven't yet taken a derivative. I've just rewritten the inner portion, right? In the next step, I'm not going to have d over dx notation because now I'm actually taking the derivative in the next step. Okay, so applying the rule, what should I be writing? 1/2 times x to the power of, we want 1/2 minus 1, right? And what is 1/2 minus 1? Negative 1/2. Now we need to rewrite this without a negative exponent. There's already a 2 in the denominator from that 1/2. And x to the negative 1/2, when that comes in the denominator, how will it come as? 1 over the square root of x, right? Because basically you could first write it like this, with a positive exponent, x to the positive 1/2, but then that's nothing but the square root function, so you might as well just put it as 1 over 2 times root x. Remember, this was another one of your messy group activity questions from the last time, maybe part C or something. Again, with this technique, it's very easy. Now, on the test, yes, I will ask you some questions using the long method, but once you know the shortcut rules, at least you can check your answer, and if it doesn't match, you always have a chance to go back and fix your work and try to catch what happened wrong there. If it's square root of x, I would prefer to see it with the radical placed in. That would be better. But usually my general rule of thumb is I just don't want to see any negative exponents. Okay, like if it was like x to the 3/2 or something in the denominator, you could either leave it like that, or you could just, like, let's just do a quick review of exponents. If it was x to the 3/2, how could you write this as a radical expression? The 3 is the power and the 2 is the root, right? So this would be the same as the square root of x cubed, correct? because 2 is the root and 3 is the power. And then there are many ways you could go about leaving this answer. You could put the 3 on the top of everything. You could take out something from the radical. But right now, I'm not going to get into that. All I'm saying is, if you have a fractional power, you can leave it as a fractional power or as a radical. But for square root of x, it's so simple. I always want you to see the square root of x in the final answer, if that's what we have. Okay? Yes, question, Sandra? Good question. Just know that if you were trying to, like, the question was, how do you know when to rationalize or not? Usually, if as the final answer, you can leave it like that in my class. I'm not very picky about rationalizing the denominator. That's like a historical reason. It was more difficult to divide by, let's say, root 3 than to multiply by root 3. So before calculators, they did, they went to great lengths to rationalize denominator. But like if you are doing something where you have like 0 over 0, you have no choice. You got to go further. There you could multiply the top and the bottom by the conjugate. But in general, if you just have like root 3 on the bottom, like it's okay. In my class, you can leave it as, like in this case, 1 over 2 root x. That's not a problem. All right. How about the derivative of 1 over x to the third power? The derivative of 1 over x to the third. So once again, let me give you a moment. Rewrite and then apply the power rule, please. So 1 over x to the third. First, we're going to rewrite it. How would you rewrite 1 over x to the third? First, just to rewrite it, it will be x to the negative third power, right? Now differentiate it. So we bring the power down. We subtract 1 from the power. What do we have? X to the negative 4. When you rewrite it without a negative exponent, it's negative 3 divided by x to the positive fourth power. Okay, so this was just a basic power rule. And before we go to the next example, I want to quickly show you where this power rule comes from. Let's see. Just know that every rule that we're learning today, if it's a rule about differentiation, it comes from that basic definition, limit as h goes to 0. So if your function was x to the n, how would you apply that definition of a derivative to that function x to the n? Limit as h goes to 0, right? If you have nothing else, no other way of finding the derivative, you would do the long way, which would be f of x plus h minus f of x over h. If you like this one, just watch this one. Don't try to write it because this is going to be messy. I'm sure it's in your textbook if you need to look at it again. This is just like an FYI. Just know where these formulas are coming from, okay? So we're going to go back to the basic definition. What should I have as my first term now for my f of x plus h? Good. X plus h to the nth power, right? Because this is x to the n we're talking about. And then minus x to the n all over h, right? Okay. Now, how do you distribute x plus h to the nth power? Let's think about that for a minute. Like, let's do a simple example. Like, what if you had x plus h to the third power? How would you simplify that? The first term is what? X to the third, right? What is the next term? You know, some of you will remember Pascal's triangle, you know, to get the coefficients from there. Like, Pascal's triangle was something like this. 1, 1, 1, 1, 2, 1. You keep adding the previous rows. 1, 3, 3, 1. So to do the x plus h to the third, you got to follow this row, right? 1, 3, 3, 1 as the coefficients row. So the next coefficient should be a 3. And you keep subtracting the power of x and increasing the other power. Like, it will be x squared times what? H to the first, right? plus the next one will be 3x times h to which power? Second, and the last one would be 1 times h to the third. Now, everything except for the first term has an h in it, does it not? And look at the second term. Now, the second term is very much revealing. So the second term, you see the 3x squared h? And we know the derivative of x cubed will end up being 3x squared, right? Everything comes from that second term. Why? Because when you expand it out in general, in terms of n, the x to the n's are going to cancel. Like if you were doing the third function, you have an x cubed coming from here and then minus x cubed coming from there. They would cancel. You're left with this next term, which is like over there, it was 3x squared h. Now, everything else has an h in it, so which means you can factor out an h from everything else that is remaining. So if you were to factor an h, so this is already gone, okay? If you were to factor an h out of this, that would be 3x squared, right? And everything else still will remain, will still have an h in it. All the other terms will have an h in them. So as h goes to 0, the h's you factored out, they disappear. They disappear. However, when you let h go to 0, everything that has an h in it is going to become 0, 0. The only thing that doesn't disappear is that term, n times x to the n minus 1. Up there, that would have been 3 times x squared portion. So that's, again, a little bit theoretical. It's going a little bit deep, but I know some of you are at the level you can understand a proof like this. So at least I want to show you where these rules are coming from. So at the end, then we say that derivative of x to the n is n times x to the n minus 1. It all comes back down from that binomial expansion of x plus h to the n. Okay, we'll go back and do some more examples. Let me clean up this a little bit. Okay, we're going to do some more examples about shortcut rules today. And there's a few more rules I want to give you. Okay, here's your rule number 4. The derivative of a constant multiple, like c times f of x, where c is a constant. The rule says, again, every one of these rules you could prove by that basic definition. But the rule says that you can pull the constant outside. You see, the c can be taken outside and then multiplied with the derivative of the inside function. So it's very different than rule number 1, right? Rule number 1 was when all you have is a constant, then the derivative is 0, right? But if you have a constant times a function, then what you have is you can pull the constant outside basically and differentiate the function. For example, derivative of 3x squared. So pull the 3 outside. And just find the derivative of x squared right now. What is the derivative of x squared? AJ, would you agree that this would be 2x, right? Derivative of x squared is 2x, right? So basically saying that keep that constant as it is and multiply it by the derivative of the inside, which is 3 times 2x, or that's equal to 6x. So what would you tell me, for example, for the next one? 5x to the 4th. What would be the derivative of this expression? So the constant remains. You differentiate x to the 4 and multiply it by that constant. So do we all get 20x cubed? Okay. And in the future, you may want to do this in one step. Just eliminate this middle step I have here. Just when you bring the 4 down, it's going to get multiplied by the 5. So you write down the 20 and subtract from the 1 from the power. That's your x cubed. Okay. All right. Another simple rule that's going to make our life easy is the derivative of a sum or difference. When you have derivative of f plus or minus g, basically you can distribute the derivative over a sum or difference. Take the derivative of the first plus or minus the derivative of the second. For instance, the example I have below is kind of like a repeat of the examples, the 2 examples from the top. So let's write down the answer. Since we have a plus between the expressions, we can go one piece at a time, basically. Differentiate the first piece plus differentiate the second piece. So what will it be? 20x cubed plus 6x, correct? So if you have a plus or minus, you can go term by term. We'll do more examples of this, such as in this example that we have at the top of the page. Let's find the derivative of 7x to the 5 minus 4x squared plus a third x cubed. This one we'll use, as you can see, a little bit of everything we've learned so far. Minus 2 over x squared plus 5 over x. I'm going to give you a little time to think about this, and we'll come back and discuss it. So I will first rewrite and then differentiate. The first three terms, there's nothing to rewrite as far as I'm concerned. But the next one, I'm going to write as negative 2 times x to the negative second power, right? And the last one, 5 times x to the 1/2 power. I kept my d over dx up front because I haven't yet differentiated this. In the next step, I'm going to not going to write it because I'm going to differentiate each term one at a time. So let me know what you guys got for the first term. 35x to the 4th minus 8x plus 3 over 3, which is going to be 1, right? Then x to the 2nd minus 2 times x to the power of, actually, there's negative 2 times negative 2. Let's make that plus 4 times x to the power of negative 3, right? We're subtracting 1 from the power. And the next one, 5/2 times x to the power of negative 1/2. Now I need to rewrite this. By the way, suppose I had one more term at the end. Say I had a 7, the 7 by itself. In the next step, the derivative of that would be 0. I don't even have to mention that in the next step, right? If it's just a constant all by itself, the derivative would be 0. What if I had something like this? Say plus 7x or something at the end there. What would the derivative be then? It would just be 7. This is like mx, right? The derivative of m times x is just a slope, or 7. Or if you're applying the power rule on that, the power is 1, right? If you bring the power of 1 down and subtract 1 from the power, you have like 7 times x to the 0. That's also 7, right? So we didn't have to deal with that in this case, but you may need to deal with that in another problem. Right now, let's just rewrite everything. Okay, with the negative exponent, it's going to go down to the denominator as 4 over x cubed. And the next one as 5 over 2 times the square root of x. Okay, did we all get the same answer here? Okay. Again, as you can see, these are not difficult, but they can get a little bit tricky. Sometimes they give you like x to the 3/2 power or something in the denominator with more fractions. You just need a lot of practice on them, so make sure you do all the homework and group activity problems, because this is kind of like building the foundation of calculus. After we learn these rules, every section we cover, we're going to be taking the derivative as the first step of a problem. So you've got to be really, really strong in applying these rules that we're learning today. Recognize this problem appearing here in red. Negative 16t squared plus 500. This was the example I used as our introductory example last class, Introduction to Derivatives. We did the long way, first numerical, then analytical. We got like negative 96, if I remember correctly. Now we have the shortcut rule. See how quickly we can get the instantaneous velocity with the shortcut rules. So to find the derivative with respect to t, what would be the derivative of the first term? Negative 32t. Derivative of a constant of 500 is 0, right? Now we want to evaluate this at the point. I can sometimes put a line here and on the bottom say evaluated at t equals to 3. Because they want to know the velocity at the third instant. Just multiply negative 32 by 3, and voila, we got it. So as you can see, shortcut rules are really great time savers. But again, we owe it to mathematicians. If they didn't see these patterns and apply these definition of the derivative, to come up with these, we would be still doing it the long way for every question. So it's definitely very, very helpful. All right, what else do I want? Okay, next we're going to take a look at a rule called the product rule. Okay. But before I go to the product rule, I want to give you a little bit of background as to why do we even need a product rule. In other words, like with the sum and difference, it was very easy. You differentiate the first term plus you differentiate the second term. Same thing with a minus. But with the product rule, something very complicated comes around. And I want to show you why we need something very complicated here. Or not so complicated, but it's a little bit more complicated than the sum rule. Okay? For example, say we wanted to find the derivative of 2x times x cubed. There's a product there, right? First, let's multiply them together. What is it? 2 times x to the fourth. Would you all agree? Okay. Now, what is the derivative of 2 times x to the fourth? 8x cubed. So we know that the derivative of the above question should be 8x to the third. But if you were trying to apply the following rule, which is differentiate the first term, 2x, or the first factor, what is the derivative of 2x? 2. And then differentiate the second piece, which is x cubed, which the derivative of x cubed is 3x squared. Would we get the same answer? No, that's why I have a question mark up here, because this is not correct. So we don't have such a simple product rule that you could differentiate the first and differentiate the second. We have a constant multiple rule. You can take out a constant, but if you have two expressions, both of which contain the variable x, there is no very, very simple rule. But there is something else, which is still not too bad, and let me show you what that other rule is. There is something that looks like this. It's a little bit more complicated than just f prime times g prime. Instead, it looks like this. If you have the product of f times g, the derivative of that product will be, basically you take one of the functions, you write it down exactly as it is, you multiply it by the derivative of the other, plus, then you swap it around. You take the other function and multiply it with the derivative of the one that you haven't dealt with yet. So g times f prime plus f times g prime. This is the rule for the product of two functions. Now, I want to see if this is really going to work with the example we had above. And by the way, because it's a summation, it doesn't matter if you swap these two around. Like it could go fg prime plus gf prime. It's the same thing because if there's a plus in the middle, if you switch those two things around, you will still have the same final result. Now, let's check the above with this rule. Remember the question 2x times x cubed? We're going to try to find the derivative of 2x times x cubed. Let's do that one more time, revisit the same example. Okay. Now, up above there, first we multiplied it, and we know the answer should be 8x cubed there. We have no doubts about that one. And you might say, well, you know, do I even need a product rule? If I can always multiply it first, then why do I need another rule? Well, sometimes multiplying it first might be almost impossible. Like say you had something like this. You know, you don't want to expand that quantity to the fifth power and then multiply. It would be a mess. It's good to know the product rule under certain circumstances. Okay, for this example, I recognize it's easier to multiply that first, but just to show you that the product rule works, I'm going to also do it now with this new rule. Okay? So my f is the 2x function here, and my g is the x cubed function. Okay? So based on the rule we have given here, what should I be writing down right now? There's g of x, which is x cubed, right? Times f prime. What is the derivative of the function f? 2 plus f of x times the derivative of the function g, which is 3x squared. So if we dissect what we have done here, this is our G, and this is our F prime, G times F prime, plus, this is our F, and this is our G prime. So we applied exactly the same formula as we see up here. What is the simplified answer? You got 2x cubed plus 6x cubed, right? Which is equal to what? 8x cubed. Is that the answer we expected to get? Look up there. When we first multiplied the 2, we got 8x cubed. That was the correct answer. Again, that means this formula really works, and we're going to use it when we're dealing with two quantities, both of which have the variable x in them. And for this particular example I gave you, yeah, you really don't need a product rule, but for some other questions, product rule will actually make your life easier. Especially once we learn something called the chain rule, you will see how helpful this rule is going to be. Okay, so let's say that R of x is equal to 3x squared plus 1. I'm going to rewrite that over here. Say R of x is equal to quantity 3x squared plus 1 times 5x minus 8. Okay, can you find the derivative of this quantity using the product rule? No. We have not studied the chain rule yet. What I said earlier was when we get to that point, you will really appreciate having the product rule. But right now, all we know is the product rule. That's what we're going to apply. So here's our example that we're working on right now. Again, I'll give you a few moments to work on. So please work on both of these questions, and then we'll come back and take a look at the answers. So we're going to apply the product rule here, right? So I'll take the derivative of the first multiplied by the second plus write down the first as it is and multiply it by the derivative of the second, which is 5. Then all I have to do is distribute this out. And then combine the like terms. Any questions so far? Did everybody get that one? Yes, Daniel. So I'm distributing my terms, this times this, and then this times that. Okay. Then I have 30x squared plus 15x squared, so that's 45x squared minus 48x plus 5. Okay. Again, it's a pretty simple rule. Let's also do the other one. So how do we find the derivative of t of x? Again, once you realize it's the product of two functions, both of which contain the variable, go with the product rule. So I'm going to take the derivative of the first. Remember, the derivative of 1 is 0, so that disappears, times the second function, plus, write down the first function as it is, times the derivative of the second, which should be what? 3x squared. Once again, the derivative of 5 is 0, so that disappears. So now we're going to multiply 2x times x cubed is 2x to the 4. 2x times negative 5 is negative 10x. 3x squared times x squared is 3x to the 4th. And 3x squared times 1 is 3x squared. So it looks like I have 5x to the 4 plus 3x squared minus 10x. Okay. Any questions about applying the product rule? All right, and guess what? There is a separate rule for quotients. So summation, adding things or subtracting things, that was really easy because you go one term at a time. That's all you have to do. When you have a product, there was a special rule for it, and yet there is also a special rule for a quotient. Now, before I go to the quotient rule, though, I want to quickly show you how did they come up with this product rule? I mean, how could somebody possibly come up with it? Basically, anytime you have no idea how to do something about a derivative, you got to start from scratch, and the scratch being the definition of derivatives, okay? So if your function is f times g, and you're applying the definition with that function, so your first term would be f of x plus h times g of x plus h minus f of x times g of x all over h. And then they applied some tricks here. Once again, I don't want you to write this, just kind of observe to see how they go about proving something like this. They add and subtract the same term. This will help them reorganize things. So they add and subtract, excuse me, f times g of x plus h, f times g of x plus h. So they add and subtract that term. And you will see how this helps. This is like adding 0, right? Technically, it didn't change anything, but it will help them rewrite certain things. So they're going to rewrite this together with this term. What's in common to both of those two terms? What do they both have? G of x plus h. So we're going to factor it out in the next step. We're going to factor out g of x plus h from those two terms. And this is what you're left with. F of x plus h from the first term. That's right there. And from the other one, if you factor that out, you've got an f of x plus let me see. Yeah, I think they did the first one with the next one. So let me just put those two together. Again, both of them have g of x plus h in them. If you factor the g of x plus h out, you will be left with f of x plus h from the first minus f of x from the second. And you do the same with the other two. Just take out an f of x from those two because that's in common, and you're left with this. What do we know about this quantity as h goes to 0? Just forget about this. What is this quantity as h goes to 0? That's the definition of what? Definition of derivative of which function, f or g? F, right? So this is f prime, and as h goes to 0, you plug in a 0 in here, you get g of x. So here you have g times f prime, okay? And over here, on the second portion, this is the definition of, this part is the definition of the derivative of g, which is your g prime. So as h goes to 0, this is like a constant which can be factored outside. So there you have your f times g prime. So that's what we have, and that's where the product will basically come from, applying that definition basically. Again, getting into theory, I know not everybody's interested, but I also know that some students, they thrive on theory, especially if there are any math majors. So if you want to see the detailed work on this, please look at the textbook or feel free to speak to me after class. Let's see. So now we're going to take a look at the quotient rule. And let me kind of do a little bit of a shortcut here. But once again, before I introduce you to the quotient rule, I want to give you an example. Say 5x squared over x. If you like, don't write this first example. I want you to start writing down here because this is where the real quotient rule is going to be. But how do you simplify 5x squared over x? That's the same thing as 5x, right? And now take the derivative of that. What do you get? 5. So the answer should be 5, right? But I'm going to put a big question mark here. I don't even want you to write this. If you differentiate the top, what would you get? 10x. If you differentiate the bottom, what do you get? 1. That is not the same answer as we got over here, right? So this is not working. So again, you need a more complicated mechanism for differentiating a quotient. And the quotient rule down here will tell us how to do that. So if you have f of x over g of x, this is how we're going to differentiate it. I want you first look at the top. Does that look familiar? Gf prime minus sg prime. If there was a plus there, it's like the product rule, right? But there is a minus. The additional thing you have to deal with is this extra g of x squared in the denominator. And I have an easy way to remember this. I'm going to write the easy way also. Maybe some of you will use it and some of you won't. Let's say that this is the higher term and this is the lower term. So I have high over low, or LOW, which I abbreviate as LO. And basically the way I remember is low D high less high D low. Now, for some of you, it might be even more confusing to do it that way, but for me, it's an easy way. That's how I learned it, I suppose. And everything, the lower one denominator square goes on the bottom. So low D high less high D low goes on the top, and everything over the denominator square goes on the bottom. But if you forget about this, if you remember your product rule, then just remember the middle one will be minus, and in the bottom you're going to have denominator squared. I must caution you though, here you cannot swap the two things on the top, right? Because there's a minus sign. With the product rule, there was no problem doing that. Here you got to keep low D high must be the first one. The lower term times the derivative of the higher has to be as your first term. Now let's see if we apply this complicated quotient rule. Are we going to come up with a 5 as the answer, which we expect to have? Let's apply it on the simple one, and then we're going to do something more complicated. Okay, so the rule says do low D high. Take the lower term multiplied by the derivative of the higher. What is the derivative of 5x squared? 10x minus higher term. What is the derivative of the lower one? 1. Everything divided by denominator squared. And what is our denominator squared here? X squared, right? If I simplify this, I have 10x squared minus 5x squared on the top, which is the same as 5x squared. There's an x squared on the bottom, so what is our answer? 5. So indeed this rule works. It looks very cumbersome, but this is the one that works, so we need to apply it. Yes, admittedly, for a question like this, 5x squared over x, I would expect you to simplify it first and do it that way. But I just did this simple example as our first one because I want to show you like solid proof, or at least an intuitive proof, that this rule really works in finding the derivative of a quotient. But could you use that rule now on another example? On this one, x plus 2 over 3x minus 1. I'm going to write it again. Find the derivative of x plus 2 over 3x minus 1. Yes, they did cancel, exactly. Because they were factor of the top, so I can easily remove those to be left with a 5 as a final answer on that one. So now we're going to find the derivative of x plus 2 over 3x minus 1. And for this one, we have no choice. We have to apply the quotient rule. Once again, take a few moments, please. Okay, let's take a look at the solution. Again, I'm going to take the lowered one, the low d high. So lower one is 3x minus 1 times d high. Derivative of the higher is what? Derivative of x plus 2 is 1 minus high d low. So the higher one is x plus 2, and the derivative of the lower one is 3. Everything divided by the entire denominator squared. All we have to do is, you don't have to distribute the bottom. We usually keep it like that traditionally as a binomial squared. Only simplify your top and be very careful with the negation sign in the middle. Make sure you distribute that over. So here we have 3x minus 1, and then this is like another negative being there, so it's like negative 3 times x, or negative 3x, and then this is like negative 3 times 2 in a sense, or negative 6, all over the denominator. As you can see, the 3x's are canceling, right? And we're left with negative 7 over quantity 3x minus 1 squared. There is nothing to rationalize because this is not a radical. And if you were asking, do we need to expand it out? We also don't need to expand it out. Again, it's very common to leave it exactly like this. Okay. Okay, I have 2 more examples, but I would like for you to get started with these examples in your groups today. Okay, let us take a look at the solutions for these examples. Again, both of them are going to use the quotient rule, starting with the top example. So we want lower term, which is 5x cubed plus 7 times the derivative of the higher, which is 2x, minus the higher term times the derivative of the lower, which is 15x squared. Notice the 7 disappears because derivative of a constant is 0. The bottom should be the existing denominator quantity to the second power. Okay, all we have to do is simplify now. Calculus portion is over. The rest is really just algebra. So multiplying 2x, we'll have 15x to the 4. I'm sorry, this was just a 5 there 2 times. So we have 10x to the 4. Then we have 2x times 7, or 14x. Now with the negative, we have to be very careful. The 15x squared, consider this like negative 15x squared because there's a minus here. So negative 15x squared times x squared, that's negative 15x to the 4. And then negative 15x squared times negative 3 is plus 45x squared. Everything over the same denominator squared. Basically, that portion I'm actually just copying over from the previous step. We already squared it. So we just copied it over. Now just combine like terms. So we have 10x to the 4 minus 15x to the 4. That is negative 5x to the 4. Then we have plus 45x squared. And then plus 14x. All over the same denominator of 5x cubed plus 7 quantity squared. And let's also take a look at the next example about using the quotient rule. Here we have ax plus b over cx plus d. Assume a, b, c, d are all constants with respect to x. So applying the same rule we just learned, the quotient rule, I take the lower expression, which is cx plus d. So again, I'm applying my low d high less high d low formula. So low d high lower times the derivative of the higher, which is just a, because differentiating with respect to x, the coefficient of x is going to be like the slope in a sense, and then b is just a constant, its derivative is 0. minus, now I want the high d low portion, ax plus b times the derivative of the lower, everything divided by denominator squared. And if we simplify the numerator, we'll be done. So multiply everything out. You have acx plus ad minus acx. And don't forget this negative distributes onto both terms. So the last term is going to be what? Negative bc, right? And everything over the denominator squared, or copied over from the previous step. So notice now the ACX and minus ACX will cancel, and what we have is AD minus BC divided by same denominator. Okay, that one looked a lot more difficult, but it was really easy if you realize that you're taking derivative with respect to x, and you treat a, b, c, d as constants. Okay, a couple extra questions. For instance, writing the equation of a tangent line to the given function at the given point. So now that we know the shortcut rules, these types of questions are not going to take us that long. So to find the slope, because anytime you want the equation of a line, you will want to know the slope, right? What is the slope of the tangent line? The derivative, right? So let's find the derivative of f by the shortcut rules. What would it be? We go term by term, and we get 3x squared plus derivative of x is 1. That's of the form m times x, where m is 1. Okay, this is the slope in general for any x, but we want it evaluated at x equals to -1. So here we have 3 times -1 squared, which is 3, plus 1. So we get 4. This is the slope of our tangent line at the point -1. To get the equation of a line, we also need a y-coordinate. So let's find f of -1. This will be our y-coordinate at that point. So plug it into the original function. Basically, we have -1 minus 1, or -2. So it turns out that the point at hand is -1 comma -2, and the slope is 4. So now to write the equation of the tangent line, we can write y minus -2, in other words plus 2, equals slope times x minus -1, or plus 1. And simplifying that, we get y is equal to 4x plus 2. That is the equation of the tangent line. Now, I would ask you to check this answer using your calculator. Go to your calculator. For y1, enter the given function, x cubed plus x. For y2, enter your equation of the tangent line, 4x plus 2. And make sure that you see at the point x equals to -1, this line will be tangent to the given function. And finally, there's one more question I'd like to share with you. Starting with number 1, f of x equals 2x cubed minus 24x minus 7. The question is, can you find out the points of horizontal tangency? Is it up? Okay. So if we're looking for points of horizontal tangency, basically we're looking for things of this nature, like peaks and valleys. That's where usually the slope will be horizontal. Rather, the tangent line will be horizontal. And what can you say about the slope at such points? What is the slope of the tangent line at such points? So when you have a horizontal tangent line, basically the slope is 0, right? Slope is 0. And what this means is the derivative is going to be 0 at those points. If the slope of the tangent line is 0, that means the derivative will be 0 at such points. So if we can use that information and set up an equation out of it, then perhaps we can pinpoint all such points on a graph. So set the derivative equal to 0. The solution to that equation will give you all such points where tangent lines are horizontal, because slope is 0 at such points. So let's take the derivative. 6x squared minus 24. We're going to set that equal to 0. Several ways to solve it. Let me factor out 6. Factor out further. Okay, normally you said each of the factors equal to 0, while 6 cannot be equal to 0. So if you said the other two factors equal to 0, you will get plus or minus 2. Now you could further take these points and plug them into the original function, and you can actually find the corresponding ordered pairs. So like if x is negative 2, plug it into the function, and you should get 25. Again, the easiest way to do this might be to use the table feature of your calculator. If x is positive 2, plug it into your function, into your calculator, and you will get negative 39. You can also graph the original function and verify that at the points that we're indicating, that you will see peaks and valleys or points of horizontal tangency. And I ask you to do the same thing for this last example. Find points on this curve where tangent lines are horizontal. I want you to work on that. I'm going to leave you with the answer. And when you're done, come back and check your answer, please. So it looks like there's going to be 3 separate answers in this case. All right, that concludes our lesson.